Hi and welcome to this webinar. My name is Erik Svenning and I'm working for DYNAmore Nordic. Today I will show you how to perform a CFD simulation using Ansa and the LS-DYNA ICFD solver. So the purpose of this webinar is to show you how to set up an LS-DYNA ICFD simulation using Ansa and LS-PrePost. And what I would like to show you today, first I will give you a brief introduction to the ICFD solver in LS-DYNA. Then we will look at how to set up a CFD simulation in Ansa. We will do some final keyword setup using LS-PrePost, and then a brief summary of what we have gone through today. So the ICFD solver is an implicit solver for incompressible fluids, and recommended LS-DYNA versions to use are either version 10.1 or 9.3, or you could also try the new version R11 that has been released recently. The solver is based on the finite element method, and it supports both 2D and 3D calculations. It has an automatic volume mesh generator, and it is very well suited for coupled simulations, both fluid structure interaction, conjugate heat transfer. It is possible to simulate coupling between CFD and DS particles, as well as free surface flows using the level set method. There is support for non-Newtonian fluids, the most common turbulence models, as well as porous media models, and now there is also a steady state solver available from version 10. The typical workflow for setting up an ICFD simulation with Ansa is to first import and clean up the geometry as you would do for any meshing task. Then you typically set the PIDs for the different boundary conditions that you use, and you create the surface mesh of the structure. The volume mesh will then be created automatically by the ICFD solver. If you are using Ansa version 18 or lower, then you can export the mesh in standard LS-DYNA format, but then you need to do some small modifications of the keywords manually or using some script. For example, you need to change element shell to mesh surface element and node to mesh surface node. From version 19 in Ansa, the ICFD format is supported, and quite many keywords are available, but typically you will still want to do the final keyword setup using LS-PrePost. As I mentioned before, the ICFD format is supported in Ansa from version 19, and to activate it you set the deck to LS-DYNA, and if you then go to Tools, Settings, and Settings Decks, there is an option for activating LS-DYNA ICFD. So if you activate that one and save the settings, then you can restart Ansa to make the settings take effect. And as I mentioned, for older versions of Ansa, then just create the mesh in standard LS-DYNA format and do the necessary conversions manually. To set ICFD boundary conditions, you go to Decks, Boundary, and ICFD Boundary, and there you have the possibility to set most of the boundary conditions for the ICFD solver, like non-slip boundary, prescribed pressure, FSI boundary. There are some of them are not yet available in Ansa version 19.0, like FS wave, for example, but most of the boundary conditions are available here. It is also possible to set initial conditions for the ICFD solver by going to Decks Initial and ICFD Initial. And if you choose new, you have the possibility to set velocity, temperature and pressure. If you here set PID equals 0, then you will set the initial condition everywhere in the domain, and this can be very practical if you, for example, want to prescribe a uniform temperature in the whole domain. By choosing turbulence, you also have the possibility to specify initial conditions for runs type turbulence models. Under DECK's auxiliaries, there is a possibility to define ICFD points. This can be practical if you, for example, want to control the size of a refinement box and you want the size of this box to change during the simulation. Then you can define ICFD points that move by means of prescribing load curves. To convert the mesh to ICFD format, you go to DECK's auxiliaries and ICFD convert. Here you have options to convert in both directions between standard LS-DYNA mesh and ICFD mesh. And currently it is necessary to release the elements from the underlying geometry for this conversion to work. And when you have done the conversion, you can go to the includes manager and check that the mesh is located under LS-DYNA CFD mesh module. For this tutorial, we consider flow around a cylinder in a channel. The fluid under consideration is water, and we choose the inlet velocity such that we get a Reynolds number of 100. At the outlet, we prescribe a zero pressure. For the channel wall, we apply no slip conditions, and for the walls and roof of the channel, we allow free slip. Next, we will use Ansa to create the geometry and the mesh, and then export the mesh in LS-DYNA ICFD format. After that, we will use LS-PrePost to do the final keyword setup. And when we have run the simulation, we will also use LS-PrePost for the post-processing. Okay, so here I have created a box with cylinder inside it, and I have created PIDs for the different parts. So we have the inlet where we will prescribe the velocity. The cylinder is inside here. We have the outlet on the other side. You have the walls, the roof, and the floor of the channel. And if we click on the different PIDs here, I have activated user sec ID, set this one to section, then we can specify that all of our PIDs will have section 1, and I have also set the material to 1 for all the different PIDs. Okay, so the next step is to create the surface mesh for the geometry, and to do that we go to the mesh module, and we first need to set the perimeter length for the different edges. So we pick perimeters and the length. We can start by picking the edges of the cylinder, and like this, and we set the length of them to 1 millimeter. Next we pick the remaining edges. This, and to speed up the simulations we can set the perimeter length here to 1 centimeter. When we have done that, we can generate the mesh. So we go to mesh generation and free. We select all the faces. For element type we need to choose triangles only, and we generate the mesh. So now we have a surface mesh of the geometry, and we need to release the mesh from the underlying geometry in order for the export to ICFD format to work. So we go to Elements and choose Release. We select all the faces, and when we have released the mesh, we can go to Auxiliaries, ICFD Convert. Here we choose to convert the mesh to ICFD mesh. Here we choose all the properties and press OK. And if we now open the Include Manager, we should see that the mesh is located in the LS-DYNA ICFD include. If the mesh would still be located in out of includes, we would need to move it to the LS-DYNA include. When this is done, we can go to File, Output LS-DYNA in order to save the mesh in ICFD format. And I should also mention that you should not output the mesh by right-clicking in the Includes Manager and choosing Output Single Files, because for the ICFD format there is a bug which is not yet corrected in Ansa version 19.0. So output the file through File Output and then LS-DYNA, and then it should work also for the ICFD format. So here I have included the mesh that we exported from Ansa and opened it in LS-PrePost. So now it is time to do the final simulation setup. And first we will take care of the warnings that we get when we open the mesh. So we see that the ICFD section and material have not yet been specified. So to do that, we go to Keyword, ICFD, and first we take care of the section. So just create a section with ID 1. Then we proceed with the fluid material. So for this tutorial we use water. Set material ID to 1, density to 1000, and viscosity to 0.001. And next we need to define curves for the boundary conditions. And here we would just have one curve with constant 0 and one with constant unit velocity for the inlet. So we go to Define and Curve, and starting with the 0 curve, we enter, take a new curve ID, we enter 0, 0, then we will run the simulation to 1 second, so take something more than 1 second, say 10, insert, then accept, then pressing new ID we can create constant 1 curve, so just changing both values to 1 here. Like this, accept and done, and we have the curves that we need. Next it is time to set up the boundary conditions. So then we go to ICFD. Let's start with the prescribed inlet velocity. So we go to boundary prescribed val. For the part ID, this is the inlet, which is number 3. And start by prescribing velocity in x direction, which is the flow direction. So there we have constant velocity of 1. Take insert. For the other directions, we'll prescribe 0 velocity. Accept and done. Now we have the inlet velocity. The next boundary condition is the 0 pressure condition at the outlet. So we go to boundary prescribed pressure. This is PID 4. Pressure 0. Insert, accept, and done. For the floor and the cylinder, we will use non-slip conditions. So we go to boundary non-slip. Here we don't need any load curves, it just need to enter the different PIDs. So we have the floor, which is PID 1, and cylinder, which is number 2. And the remaining walls that need boundary conditions are the roof and the walls of the channel. So here we will use free slip conditions. So starting with first walls, insert, and then the roof, accept, and done. Now we have set the boundary conditions. Now we also need to set time step, end time, and define some output. And starting with the end time, we go to ICFD control time, set the total time to 1 second, and for the time step I just set it to 0.01 second. You could also leave this blank and instead specify the CFL number you would like to have, and then the solver will adapt the time step for you. But here we will just specify a constant time step. So accept and done. Next we need to specify some output. So then we go up to database and binary D3 plot. We can set the time interval to 0.1 second. And now we are almost done with the simulation setup. We also need to specify the volume for the fluid solution and set some settings for the mesh. So for the volume we go to ICFD part vol, and we choose the section and the material we created earlier, and here all the parts that we have created form the volume, so we just choose all 6 of them. So insert, accept, and done. And now we also need to define some mesh settings, and here, since we have provided a surface mesh, we need to tell the volume mesher how to create the volume mesh. So we go to mesh volume, and here all the parts will form the mesh, so just select all of them. We need a volume ID, so volume ID 1, accept. Oh, forgot to click insert, so specify all 6 of them, insert, accept, and done. And if you like, you can also specify boundary layers on some surfaces if you like. You can specify mesh refinements in certain regions, but here we will leave that as default. Now the simulation setup is complete, and it just remains to run the simulation using, for example, LS-run and then to open the result files with LS-PrePost. I will not go through the post-processing in detail here, but I have included some snapshots of the pressure and velocity fields. So to summarize, in this webinar we have set up an ICFD simulation using Ansa and LS-PrePost, and a few final remarks here. First, regarding the mesh generation with Ansa, if you are using version 18 or lower, then you need to do some manual conversions, like changing node to mesh surface node in the mesh files. And also for the conversion from part to ICFD part to work smoothly, then you go to section shell and activate user sec ID. I would also like to mention that here we have created the surface mesh in Ansa, and then we let the ICFD solver create the volume mesh automatically. And this is the default approach, and this is how you have to do it if you have FSI problems with moving boundaries and remeshing. If you have a problem where you from the beginning know that the mesh will not move, then it is possible to have a user-defined volume mesh, but then only TET elements are supported. We also made some final keyword setup with LS-PrePost, and this was what I wanted to show you today. And if you have any questions or comments, you are welcome to contact me at erik.svenning@dynamore.se. And by that, I would like to thank you for your attention and see you next time. Goodbye.